Good afternoon to everyone. Welcome to the third episode of our webinars. Today, my colleague Davide and I are going to talk about sustainability and circular economy, two of the most important and urgent topics of our century. And we will do that with a particular focus on technical thermoplastics. So let me start with some examples of technical applications. Here you see an electric motor stator. In a very simple way, an electric motor is made by two parts, a stator that stays still, and the part that rotates is the rotor, which is placed in the central cavity that you see in the picture. And on the cavities on the sides of the stator, you should imagine metallic coils where an alternate electric current flows, generating an electromagnetic field, which makes the rotor rotate. So in this way, the electric current is transformed into kinetic energy, so movement. In this particular case, this object is made by metallic plates on both the outer and inner part of the object. And the red one is a thermoplastic compound, a technical compound which is self-extinguishing, structural, because you should take into account that the coils are really tight and they create a stress on the material that therefore need to have a high strength. And then it also must be electrically isolating, because of course the current should flow in the coils only and not in the body of the part. Here the polymer is overmolded on the metal, so it's very difficult to separate the two materials, and therefore we can ask ourselves, how do we recycle this material, especially now that we have a steep growth of the electric vehicle sector. This is an important issue, because we will have a lot of these objects, and how can we recycle them when at the end of their life cycle? Because we cannot separate the two materials, so one option might be to melt the metal to recover it, and by doing so burning the plastic, but this is not the optimal alternative, because we are losing material. So one challenge is to design this object in a better way for recycling. The second example is this magnetothermic switch. This device is present in every house and every building because it's the safety device that stops the current when we have a short circuit or an overload, and which are two situations in where we have a fire risk. So this object is extremely important for safety, but because of its complex function, it's itself complex. You see that it's made by at least 4 different compounds, several metals, and then we have the cables and the sheets. And it's nearly impossible to separate all the components. Even if it was possible, it would be so complex and so expensive that it wouldn't be convenient. So here you see another example of an object with that is, because of its function, really complex, and the great challenge is to find a way to design this object to take into account also the end of life. So we see that technical compounds are strongly related to specific application. Therefore, we cannot separate the material from the application, which means from the way we use these materials, our way of life, our economical model, our lifestyle. So to further understand how entangled these two things are, let me go through the history of plastics very, very briefly. We start in the late 19th century with the first synthetic plastic materials. One was celluloid. Celluloid was invented to replace ivory in billiard balls. And consider that ivory is taken from elephants by killing them, and it's very harmful, and it's expensive. So by finding an alternative to this material, we had two aspects, innovative aspect, let's say. One was environmental, so no more killing elephants, and the other one was social, let's say, because since ivory was so expensive, billiard was a game reserved to wealthy people, rich people. With celluloid, it became cheaper and therefore affordable by poorer people. So we see a social aspect, a social consequence of a new material. Then we have the example of bakelite, which replaced wood in many applications, cellophane, and then nearly 100 years ago, we can say that we had the start of the plastic industry. In 1935, nylon was made. This is another important example because nylon replaced silk. Silk was a natural fiber which was quite expensive to get, but there were no alternatives. And consider that, for example, during the First World War, the parachutes were made with silk. And but if we want to consider a more common application, let's consider tights. So tights made in silk were really expensive, so only rich women could afford them. With the invention of nylon fibers, they became cheaper, and every woman could afford these object, these tights. And then nylon became the so much useful material that we know now. It's used in many applications, and we will see some of them later on. Then we have the start of vinyl records industry with the production of PVC. Of course, this color picture is not from 1939. It's just to give you an idea of what we're talking about. Here we have another important social consequence. All the music industry that we know now started from this, because with vinyls, people could listen to music at home, even if they couldn't afford to hire a musician, even if they couldn't play, even if they couldn't afford to go to the opera or to the theater, they could listen to music. And this started the industry because more people, the audience became bigger, and more musicians could make other people to listen to their voices. We then have the invention of PET, another synthetic fibers, Formica, and then we arrive to the first plastic bottle for sparkling beverages. Another important date is 1954, when Giulio Natta made isotactic polypropylene, which is the polypropylene that we know now. Isotactic refers to specific conformational order of the polymeric chains that allows polypropylene to crystallize. Earlier, we had atactic polypropylene, which has no Horden, so it was amorphous, and it couldn't. It was useless, basically. Let me say so. Isotactic polypropylene is the useful material that we know now, and that in Italy at least became famous thanks to Gino Bramieri's sketches in the show Carosello. It's something very typical of Italy, but if you're curious about, I think it's worth take a look at it, because Carosello was a brief show in the evening in Italy, and where there were 3 or 4 sketches whose aim was to advertise a product, and in this case, the product was Moplen, which is the commercial name of polypropylene. And Gino Bramieri, in his sketches, showed how this material changed the lives of housewives, but of people in general, because it was lighter, it was cheaper, it could be used to make many different objects, and it was the emblem of modernity, of innovation, and so it was something positive, let me say. Nowadays, technical thermoplastics are used in many different applications, almost everywhere. We saw the electric industry, but also electronic, the house appliances, transportation. Also, because of safety reason, we have very strict standards in the railway sector, for example. All the electric vehicles, contact lenses, and also lenses for eyeglasses, every kind of sport, in the medical sector. And please note that all the advancements in medicines were possible also because they were supported by innovation, machines and technologies. And many of these technologies, many of these machines couldn't be made in other materials. Plastic is fundamental in this application, cannot be replaced, and in many applications is still the best alternative. The lighting sector, and also we landed on the moon thanks to plastic, because the spacesuits were made in plastic. So we see that plastic is everywhere, is in every application, and cannot be separated from our lifestyle. So when we consider the plastic issue, the plastic problem, if we want to solve that, we must consider how we use them and all the activities that we do in our lives, and also how our economy works. I think this quote is quite significant. So in the 1950s, this guy said, "The future of plastics is in the trash can." Consider that we are after 2 world wars, the economy needed a boost, and this guy saw in plastic a way to do that, because plastic bottles were sold for a little money. Therefore, people didn't value them, because if you pay something a little, you think that it's not that it's worthless, or that it's not so valuable, and you don't mind to throw it away. So he said, if I produce something that people will throw away after a short period of time and then will buy another, it's perfect. I will sell a lot of those products. And now this applies to nearly every product on the market, because our economical system relies on continuous production. It would collapse if production stopped, and therefore we need to have a demand that absorbs this offer, and this is done by creating products which are which breaks down after a defined period of time. This is called program obsolescence. That maybe just a part breaks down, but it's impossible to replace it, or it's so expensive to do that it's cheaper to buy a whole new product. And this led us to an overproduction that is the main cause of our pollution problem, let's say. And because of this overproduction, people's perception of plastic became negative. So especially if we consider single-use plastic. So when we ask people which are the concepts that they associate to plastics, this is our answer. We literally did that, and we see that we get words like pollution, waste, toxic, junk, but also packaging, bottles. So we see that microplastic, we see that this idea of something negative is connected mainly to single-use plastics. But if we take a look at the world plastic production in 2021, so last year, we see that only 45% is packaging. So this perception is based on a limited part of the picture. And if we, moreover, if we focus on the packaging sector, in the last 30 years, we had big improvement, especially in Italy. It's not so in the whole world, but still we are working on that. But we also see that is a big share of the cake which is not considered. And in this part we have the technical compounds, which, as we saw, are embedded in these kinds of objects, which are really complex. So how can we recover these materials which are found in such complex objects? People ask plastic producers to take some actions which are based on these distorted perceptions. So compounders, the plastic producers, are asked to eliminate plastics, but this is not possible because it's not the right solution. We saw that in some cases there are no alternatives to plastics. In other cases there are, but plastics are still the best option. Then compounders are asked to use bioplastic or use recycled materials, which is not always possible. At the same time, the industry asks also for strict material requirements connected to the application, compliance to standards, specific colors, which are not always possible to achieve. For example, if we use recycled materials obtained by several colors, then we get a dark mix, and we cannot achieve specific colors if we use that mix. And then a target cost. So maybe we make the best material, but then it's too expensive, and we cannot sell it. So we can say that compounders are squished between the requests from the market, and by market I also mean people, which are on the left, and then from requirements from the industry on the right hand. So in this scenario, I ask you, Davide, which are the impacts of compounders and what can they actually do to reduce them?
Thanks, Anna, for perfectly explaining how important plastic are, but as well how plastic material are associated with pollution. And when we think about pollution, it is very important to consider the impact on climate change. And we know that plastic materials are fundamental for many applications, but as well, plastic production is responsible of about 5% of global carbon dioxide emissions. Moreover, we know that this figure will grow as part of the economy will decarbonize, unless plastic producer will take action and start to reduce the emission related to the manufacturing of plastic materials. And then what we can do as compounders or as converters to reduce this type of emission. Certainly, if you look at the slide on the left, Scope 1 emission in jargon, when we think about a chimney, are the most evident, and in some cases were also the first to have been tackled. For example, by converting part of the plant from fossil fuel use to electricity use. However, we must consider also Scope 2 and Scope 3 emissions. So for a compounder, mainly the emissions related to the production of the electricity that is used to power extrusion lines. And for Scope 3 emissions, mainly the emission related to raw materials productions. And there has been efforts in recent years to decrease, beside the direct emissions, also the emissions related to electricity use. For example, by using electricity from renewable sources. If you want to go deeper into the subject for LATI, you can find the link in this slide for our corporate sustainability report. If, however, we follow the components of a plastic granules from the production of monomers and of additives till the gate of the compounders, we have verified how, for technical thermoplastics, the production of the base polymers and of some additives are responsible for a very high percentage of the CO2 emissions related to a product. Similar consideration can also be made for the injection molding process. Therefore, it is important to reduce the emissions related to the conversion processes, but it is also very important to focus on raw materials and especially on polymer from fossil sources. Hence, our attention will now be on how to have a more sustainable raw material sourcing in the supply chain. Two possible approaches to reduce the emissions are the use of recycled raw materials or the use of renewable raw materials, sometimes also defined by the prefix bio, like biopolymers or biomass. Focusing now on recycled material, two possible approaches are mechanical recycling and chemical recycling, both from post-industrial feedstock, post-consumer feedstock, or in some cases, a mixed feedstock that can be used in the same process. If we consider all the possible recycled polymers, we will now have as a case study a key polymer for technical application, that is polyamide 6. Polyamide 6, or a kind of nylon, has been used for many decades as a post-industrial recycled material from mechanical recycling, mainly from textile industry scraps. There are indeed many advantages in the use of such type of materials in terms of sustainability. However, we have to consider that there are two main issues. One is that if you also have a look at the appearance of the granules that are kind of yellowish, for very stringent customer requirements, only a partial substitution is possible in some application of the virgin polymer. And the other main issue is the competition in the use of this type of material with the textile sector, because in the past the textile sector was glad to have this type of scrap used by the plastic sector. But nowadays they have also very challenging targets regarding recycled content, and they use a much higher amount of this type of materials. So if we think now about the challenge of availability of polymers from recycled sources, and we think about it as citizens, we may think that packaging waste is the solution. And indeed, in many cases, it's possible to use this type of materials. However, if we look now which polymers are present in this type of waste, we see that mostly are polyolefins, PET, with only around 1% of nylon. So it is possible to upcycle polyolefins for high performance application in some cases. These in particular using a specific formulation and a specific process, but in other cases is not possible. And we also have to deal with a waste that is not always the best. And in this, as my colleague explained, we have to rely more and more on new approaches. For example, the eco-design of the packaging to reduce undesired volatile organic compounds present in some of these waste streams, and to reduce the presence of pigments that might hinder the recovery and recycling of this type of materials. Moreover, we have to consider that even if we sum up and we increase all the possible material that we can obtain from mechanical recycling, and we compare two targets of the industry regarding recycled content, in some studies they have reached the not so good conclusion that they may be not realistic unless we find a new way of recycling plastic materials after end of life. And this can be done in several ways. One possibility is to start to recycle materials and products which were not considered recyclable. We have seen this part many times in this presentation, and this is a typical example of mixed plastic with metals, a very complex part, and also maybe also the plastic material is not very simple. And one can think, okay, but in the future, we will redesign this part with eco-design, for example, removing the metal, and this will simplify the recovery process. This for sure we will need to do. However, we will also need to consider that this part lasts many years. So for many years, we will have a legacy of waste of this type with a flow of compositional information that is not always the best, a cost of the recycling and recovery processes that can be too high, especially if you consider, for example, the need to separate the metal from the plastic, and quality and performance consideration, as well as strict regulations. So, what can be the main enabling innovation to try to increase the recycled content? Most likely, only advanced recycling technologies, mainly chemical recycling, will be able to increase the share of polymer coming from recycled sources to a predicted share of around 70 to 80% of virgin polymer by 2030. And indeed, already now, we see chemical recycled polymers produced at industrial scale. And what is important to remember is that there are flows of polymers and that could not be recycled mechanically. So we are adding new quantities of polymers. It's also good to mention that part of these processes produce pyrolysis oil, sometimes used for the production of polymers and sometimes in other interesting applications, but that are different. In any case, today we will focus only on processes that bring to new polymers of interest for technical application. And as a main case study, we will discuss polyamide 6. Polyamide 6 can be produced via chemical recycling with a back-to-monomer process or via mechanical recycling. It is true that many studies highlighted the impacts of chemical recycling and shown that these impacts can be higher as compared to mechanical recycling. However, there are two great added values of the chemical recycled polyamide 6 in terms of flexibility. First, flexibility of the input. As we have discussed before, it's possible to recycle with chemical recycling materials that is not possible to recycle with other technologies. And the second is the flexibility of the output. So that is possible to substitute virgin polymers even with a high percentage of the chemical recycled polyamide 6 without affecting too much, or in some cases without affecting at all, the property of the final object. And these we need to compare with what we have seen some slides before with a recycled polyamide from the textile sector to consider the difference of the two approaches. Now, if we can say, is this a solution for all issues of the plastic industries? Clearly is not, because the availability of polyamide 6 from chemical recycling is limited, and moreover, cost consideration makes this the use of this material feasible only for some application. One of the greatest challenges that the plastic industry is facing is the recovery and the obtaining post-consumer recycled polymers from electrical and electronic waste. Why it is so important? Because in this type of waste we can find a lot of technopolymers. So in principle it is the perfect source of recycled polymers for technical application. However, we have to consider that we have a combination with metals and in some cases also glass and chemicals to be carefully evaluated. Again, also here, our role as a producer and compounders is to guide the supply chains toward a better design of new objects. But if we discuss about what we can do today, we have to remember that these impacts will affect the supply chain and the recovery of the materials only after many years, when these products will become waste. So also this is a solution in the long term, a partial solution, but is not the solution. What is then the ultimate solution? In some cases, a lot of promises have been done regarding biopolymers. And indeed, there are undoubted advantages in the use of biopolymers, including the presence of technical equivalent solutions, for example, biopolyolefins. There is, however, if we compare the graph on the left, that is the global production capacity of bioplastic as given by a European bioplastic, and the demand on the right, we figure out that there is a challenge of scaling up of the production. And hence we are very far from covering the global demand with biopolymers. Besides that, we have to consider that biopolymers are also subject to strong competition between different application sectors, with the packaging sector now accounting for almost 50% of volumes. In particular, by exploiting the compostability of certain biopolymers that is perfect for single-use application. But if we now come back to technical applications, we have to consider that only a fraction of the biopolymers produced are high-performance polymers, and so beside availability, we have to evaluate the performance, the cost, and the sustainability, both of the polymers and of the precursor, with in some cases complex considerations. Besides biopolymers, you may have read in the news titles like the new plastic from bamboo solves the plastic pollution problem. I have to say that it is true that by adding some biomasses during the extrusion or during the conversion processes, is possible to obtain benefits. In particular, it is possible to increase the availability of renewable raw materials because we are decreasing the need to use virgin polymers or to use biopolymers that are limited. However, we have to consider first that some of these news are misleading in the sense that they refer to plastic made by biomass, while usually is with the addition of biomass. And then we have to consider as well that this is only a partial solution because it's suited only for some application. And also in this case, different type of cultivation may be different in terms of sustainability. So you may now have a feeling of my opinion that is that nowadays there is no solution, not a single one that solves all the problems. There are a number of possible solutions that are good for certain applications, and certain possibilities that may be unlocked in the future thanks to innovation. The challenges are many, and the only things that a company like us can do is to open up to the world of academic research in an open innovation approach. And this is particularly important also because we have to consider that many companies are small and medium enterprises which lack the internal know-how to face this type of very complex challenges. As LATI, we are involved in some of these projects, and I invite you to continue to follow us because we will have updates regarding the result of this project. Besides that, we have also some R&D activities regarding new approaches to innovation for eco-design, and my colleague will now explain better.
Thank you, Davide. So we saw some actions that we can take as material producers. We analyzed the current situation and possible issues that we might have in the future. And we asked ourselves, is this enough? Of course not. This answer is not because we are pessimistic, but because we must face the reality that compounders are not isolated players, but they are part of a production chain that goes from the raw materials producers to the end user. So we cannot act alone and try to solve the plastic problem. We need to cooperate. We need to work together with the other players to find solutions, because compounds are developed according to clients' requests. And clients define the material requirements in the design phase according to the application. Therefore, materials alone cannot be sustainable. They can be sustainable together with the whole process and the whole application. We cannot make the perfect material that solves all the problems if then it's used in a bad way, if then it cannot be recycled, it cannot be recovered, and it becomes waste in a short period of time. This leads us to the concept of eco-design. To understand better what we're talking about, let me show you a graph simplified of a production chain and all the actions that we can take. But first, let's go through this definition, let's say, of eco-design. So, eco-design considers environmental aspects at all stages of the product development process. So, not only the material production, which is of course important, but it's not the only stage that must be taken into account. Striving for products which make the lowest possible environmental impact throughout the product life cycle. This means that we should consider the impacts of the products not only basing on the material. So when we design a product, of course it's important the material selection because of the properties of the product required for the application, but also because we want something that impacts the least possible. But it's also important how we use that object and what is its end of life. So for example, during design we can ask ourselves, what is the business model, let's say, the idea, the concept of this object? Can we share it among more people? The most straightforward example is car sharing. So I own a car, but I only use it for a limited period of time during the day. The idea of car sharing is to switch from ownership to usage, to sharing, so that we can use a car for the most time possible of its life. So when I don't use it, someone else can use it. It's not parked waiting for me, but someone else can use it. This is sharing. But then other actions can be taken. We can maintain our products, try to repair, refurbish them. So in the design phase, this is translated in create an object that can be disassembled, that is easy to repair. If a part breaks down, we can just take it away and substitute the single part, and doing so must not be more expensive than buy a new product. It should be cheaper. And so, for example, we can design products which are which have screws instead of glue. Just one example, and this is also useful in the recycling phase, because if something is easily disassemblable, we can just separate it in its own in its single parts, which are made of different materials, and then recycle these parts. So many actions can be taken, but of course this is difficult. It's not so easy, otherwise we would have done it already. And it's just one action, one piece of a bigger change that represents the most severe problem and yet the most stimulating challenge of our century. And everyone can play a part in this change. So let's wrap up shortly what we saw in this webinar. So we firstly ask ourselves, does people's perception matches reality? We saw that public opinion is focused on a limited part of the picture, which is usually single-use plastic. And because of that, all plastics are blamed when they actually fostered economic growth. And for many applications, there are no valid alternatives. Plastics are still the best solution, and in many cases, the only possible. And then we asked ourselves, what can plastics producers actually do? We saw that we can use bioplastics when it makes sense, try to use the most recycled materials as possible, make durable compounds that are used for decades, and then, very important, to cooperate with all the players in the production chain. Can we recycle our way out of plastic waste? We saw that huge improvements have been made in the recycle stream, but we should keep working on that to try to further improve what is already been done, and to try to recycle also the technical compounds and all those plastics which are not considered now. We should try to change our way of life, our production and economic models, to avoid waste to be generated in the first place. This can be done by focusing on eco-design, and also by favor sharing, maintaining and repairing over recycling. So try to do all these actions, and then when all of this is done and no more possible, recycle the object. So I hope you will find something interesting and inspiring in these bullet points. This is the end of our webinar. We recall that we already had 2 webinars. If you missed that, you can send us an email to get the recordings. And also remember that on December 14th, our colleagues Agnese and Federico will talk about design with thermoconductive materials. So don't miss that. Really interesting. And now, if you have questions, we are here. Maybe we will wait a couple of minutes so you can write them down in the chat. Okay, so we have some questions. I will start with the first one. We are asked, are there any plastic materials or products that can't be recycled even in the future? Well, there are materials which are difficult to recycle if we compare them to thermoplastics, because the advantage of thermoplastics is that they can be reprocessed. And this is not possible, for example, for thermosets, which cannot melt. So the alternative is to burn them to recover energy. Or the same is for cross-linked rubbers. So, for example, tires. In this case, we can burn them down, or we can also mill them, cut them, and use them as lower value materials in other applications in the construction buildings and this kind of applications. But we can for sure work on them. For example, there are a lot of thermoplastics rubbers which and people are working on them to replace cross-linked rubbers in the tire sector. Of course, this is not easy, but yeah, they're working on that. So hopefully in the future we will have alternatives.
Thanks, Anna. I see another interesting question. For example, one is about PA6 and the carbon footprint as compared to materials like polycarbonate or ABS. I have to say that this is a quite complex question because we are a compounder. So first we have to mention that we would need to compare two materials with the same technical function, let's say. So maybe a polyamide with a specific glass fiber content or flame retardant content as compared to a technically equivalent compound based on a different resin. In any case, this is one thing. The second thing is that CO2 emission are one part of the story. Recycled content for circularity, as we have discussed, is also important. So what I can say is that for PA6, we have quite established possibilities both for mechanical recycling and chemical recycling. But the carbon footprint argument in some cases may lead to the conclusion that PA6 from virgin polymers can be higher in some cases as compared to other polymers, but again, it's all up of what is the final application, how long will last, and if it's possible to substitute PA6 with another polymers without making a part that is less durable or that just does not meet the technical requirements. So then another question maybe for my colleague Anna, which works for the product development teams. Can you tell us, Anna, which material are you developing and are available already now with recycled material, in particular our core business flame retardant materials?
Yeah, there is this question about that. If we have materials with recycled content, for example, flame retardant materials, yes, we do. We have some grades based on polyamide 6 and also on polyamide 6,6. Keep in mind that it's difficult to obtain compounds which are based on 100% recycled content. So it's completely or apart from recycled content. But yeah, right now we do. We also have something based on biopolymers, which is another questions that we have. So I'm joining two different questions because they also asked us if right now it's possible to have biopolymers, which are flame retardant. On this aspect, I must say that these biopolymers are bio-based, so obtained from renewable sources, but then they're equal for properties to fossil-based materials. So yeah, we also have that.
Thanks. And I see some other question is about the use of a mix of recycled material with virgin material, more in general, I think, as compared to the example that we have seen. And yes, indeed, we have seen that especially the market at the moment really appreciate this type of approach, mainly also due to the fact that we need to balance cost, performance, and sustainability. Clearly, using a very low recycled content, for example, is not something that we would advise unless the formulation is better as compared to other formulations in terms of sustainability, because, for example, there are also a biopolymer added or biomass. In any cases, I just wanted to add also for the question before of the carbon footprint, we are scaling up our efforts of understanding more about the LCA of our materials, and we are cooperating with and funding a PhD student at a local university to assess LCA for some of our key raw materials families. Because what we know is that carbon footprint is one aspect, but it is good to be given as a first key aspect of the material, but is not clearly the only one to be considered for a material.
Okay, so it's past 5. We have some more questions, but we will let you go, and then we will answer to the other questions by email. So don't worry, your questions will be answered. If you didn't manage to write them in the chat, or if you have any issues you want to discuss with us, you can send us an email. Here are our contacts, so you know how to reach out. Yeah, that's it. So we wish you a nice evening, and thank you for participating.
Thank you, and see you soon, maybe in another webinar or maybe here in Vedano.
Bye.